Right, now we have our second video. We're going to start off with two examples and then get into some more definitions. And then we'll end off with a couple more examples. So we're going to jump right in here. For our first example here, given a right triangle with legs of 7 feet and 12 feet, find the hypotenuse. Again, remember, the legs are the smaller pieces and the hypotenuse is going to be the biggest one. So this 7 feet and 12 feet, those would be our A and B values. So when we're plugging into our Pythagorean theorem here, remember, a squared plus b squared equals c squared. We can just plug in the pieces we know. 7 squared plus 12 squared equals c squared. The hypotenuse, c, is what we're trying to find. Okay, simplifying all of our pieces here, 7 squared is going to be 49, 12 squared is going to be 144, and again we still have c squared, that's our unknown value. 49 and 144, we can add those and simplify to 193 equals c squared. Now normally, if we need to take the square root to get rid of that, that squared part of our c, the square root is going to cancel out with our squared. So we would just have c. This side over here would have the square root of 193. Normally we would say that we can have a positive or negative. Again, the square root of 9 would be 3 or negative 3, because negative 3 times negative 3 would be positive 9. In this case, because we're talking about the sides of a triangle, we can't really have like negative 3 feet as a side. So in this case, we're only talking about positive. We can only have a positive measure here. So we don't need to say positive or negative. We can simply say c equals the square root of 193. That's kind of a little more exact. Or you can use this squiggly equals, that's saying approximately, or c is approximately 13.892. And you can round to just a few decimal points. That's all right. You don't need to go out too terribly far. Both answers are acceptable. Neither one is necessarily preferable, but it's actually more exact to just leave it as the square root of 193. Let's go into our second example. Find the missing side. Now again, we have a right triangle. Here's our right angle. The one across from it is going to be the hypotenuse. So 8 and c are going to be our legs, our a and our b value. So when we plug everything into our Pythagorean theorem, we would get 8 squared plus x squared equals 14 squared. Now again, just like before, we need to simplify everything. 8 squared becomes 64, x squared stays as x squared, and 14 squared becomes 196. To get x squared alone, we have to subtract 64 from both sides. When we do that, we'll get x squared equals 132. Again, taking the square root of both sides, we'll be left with x equals the square root of 132, or x is approximately 11.489. We're going to go over a couple more definitions here. An altitude. An altitude is a certain segment on a triangle or inside of a triangle. And it says that we connect the vertex, so one of our corner pieces of a triangle, to the opposite line that is perpendicular to it. So in a sense, the altitude is like the height of a triangle. So you can see in this triangle, I'll draw it a little darker in blue, A, B, and C. That's our triangle. We start at a vertex up here at A and come down to the opposite side. As we come down, it has to be perpendicular, so it has to come at a right angle. That length there, that red line, that's going to be the height of the triangle, or the altitude of the triangle. Now, this one here, it's a little bit crooked, so I'm going to show you one that was drawn like this. Let's say this is our triangle, and I wanted to draw the altitude, from this vertex up here. Well, I'd have to come straight down to the line that contains this segment, okay? We wouldn't say the height is somewhere over here. That doesn't necessarily make sense. We have to continue the line over in red here, that dashed line, and bring our line down so that it intersects it at a 90-degree angle. It's perpendicular to it. Now, this red length, this is going to be the height or the altitude. Okay, so it's not always like right inside of the triangle like it was in this case. Sometimes it can go on the outside of the triangle, but it's just a way of saying the height, basically. An angle bisector. This one should be review. An angle bisector is a segment that cuts an angle into two equal angles. So, in this case, we can see this angle is exactly as big as this angle. So the dashed line here, going from B to X, that is our angle bisector. It cut angle ABC exactly in half. So it's an angle bisector. A perpendicular bisector is a line that cuts a segment into two equal segments, and it is perpendicular to that segment. So this picture is a little bit darker. I'm going to use my own picture over here. Say we have this line AB, and I have this line starting over here. We'll call this CD, and it goes through AB right here in the middle. We'll call it E, so that A to E is exactly as big as E to B. So CD would be considered a bisector. It's a segment bisector because it cut AB exactly in half. The difference between CD and a perpendicular bisector is that CD is not perpendicular. We can tell these angles are not going to be 90 degrees. So how we can make a perpendicular bisector, it still has to go through that exact middle point, but it has to be straight up and down. It has to be perpendicular to AB. Now our blue line, that would be a perpendicular bisector. It cuts AB exactly in half, and it's perpendicular to it. Perpendicular bisector. I know these might be a little bit difficult to see. They should match up exactly on your notes, though. So we need to identify each special segment and what we know from that information. Okay, so we have triangle ABC, and we have this segment AD cutting down so that we have a right angle here. Because it's cutting down at a right angle and hitting that bottom line, this would be an altitude. So what do we know from that information? We can say that AD is the altitude, or is the height of that of the triangle. We can also say that AD is perpendicular to CD or to CB. But that would be most of the information that we know. For our next one, ABC again is our triangle, and we have this line that is cutting it right there. It is perpendicular. We can see there's a little box here, and it cuts these exactly in half because they have those segment pieces there. So it's perpendicular, and it's cutting that CB exactly in half. So it's a perpendicular bisector. Again, what information do we know from that? We know that from C to D is going to be exactly the same length. We know D to B is the same length as C to D. We know that that line is going to be perpendicular, and that's kind of the information we know, or the information given. Let's look at our third triangle. Again, it's ABC. We have the segment going A to D. These segments on the bottom, they are the same length. So C to D is the same as D to B. So we call that a segment bisector. One thing that we know for sure, D has to be what's called the midpoint, in the exact middle. In fact, this D here and this D here, we'd call them both midpoints, because again, they cut that bottom piece exactly in half. And that's really, again, that's the implications, or that's what we know from that segment there. Our last one, again, our triangle ABC. We have this segment A to D, and it's cutting this angle, CAB, oh, that's getting really off, into two equal angles. Just going to erase that actually. Because it's cutting the angles or cutting the big angle so that the two angles are exactly equal, that one would be an angle bisector. Cuts it exactly in half, so we have two equal angles there. That one is an angle bisector. One more definition here. We have mid-segments. A mid-segment in a triangle is a segment that connects two midpoints in a triangle. So in this case, A is a midpoint because we have these two segments being equal to each other. B is a midpoint because this segment is exactly as long as this segment. So from A to B, that is called a mid-segment. Okay, that's what the definition is, or that's where it would be. Now, something special about mid-segments, it's very nice to know, mid-segments are parallel to the opposite side and are exactly half its length. So we could say that this is parallel to this, and if this whole thing was 12 feet, this one up here would have to be 6 feet. It's exactly half, and it's parallel. So it's nice to know that definition. That'll help us with a lot of our examples or a lot of our problems. So for our first example, we have a triangle ABC, and we have extra points on it, P and Q. We have a lot of lengths here. We have 8, 8, 9, 9, and 6. And we need to find out what X would be. Now, because P cuts AB exactly in half, we have 8 and 8. P would be a midpoint. Same thing. Q cuts CA exactly in half, 9 and 9, so Q is a midpoint. Because those are our two midpoints, and they are connected by this line, that would be a mid-segment. This mid-segment is going to be parallel to this line and exactly half of its length. So if this one is 6, X equals half of 6, so X equals 3. We don't know if that's feet or centimeters. We just know X would have to be 3 in length. All right, we have our very last example. Same thing, we have our triangle. We're given that this segment is just as long as this segment. This one is just as long as this one. So this point and this point are midpoints, making this segment a mid-segment. Okay, that tells us it's going to be exactly half of this over here. There's two ways to write that. We could say half of this is going to be this one, or 2 of this equals this. That might be the easier way to write it. So as we work our problem out, let's use the 2 of the mid-segments would make the longer side. So 3n plus 12 equals 2 mid-segments, or 2 times n plus 14. Now using our distributive property, we can simplify this side to say 3n plus 12 equals 2n plus 28. Okay? Now we need to start moving things together, get all our n's on one side and all our constants on another. So if we subtract 2n from both sides, we would get 1n, or just n, plus 12 equals 28. And subtracting 12 from each side, we would get that n equals 16. So we have solved for our missing variable n. And that should be the last of our examples.